Good morning. I'm going to be talking more about black hole thermodynamics. Okay, I've done a bit about this in the past. I'm doing it here under the guise of general relativity. I'm going to call this Gen Rel 25. Now this Gen Rel 25 is getting a little bit more into the area of physics than Riemannian geometry, Riemannian, call it what you want. What I want to do in this particular session is address all the units that are going to be cropping up in the thermodynamics of black holes, because we're going to be looking at the thermodynamics of black holes. For example, S is the area of a black hole with a Planck length squared with a factor of 1/4 and a constant Kb, Boltzmann's constant. So what other constants will we have? We will have G, H, H cross, C, fundamental unit of charge, Stefan Boltzmann's constant, the universal gas constant, Avogadro's number. Anything else? I guess that's it. So let's begin with the G. Now G is usually written in terms of Newton meters squared over kilograms squared. Newtons are kilograms meters over seconds squared, and meters squared over kilograms squared. So it gives me meters cubed over seconds squared kilograms. I'm going to have this up here. Because we like to write everything in terms of base units. And where does this crop up? Gives the force of gravity, the strength of the force of gravity between the following. If I held 2 kilogram masses a distance of 1 meter from each other, the strength of the force between them would be this. And it was measured by Cavendish in 1798. Okay, the universal constant of gravitation, of course, is not the same as the acceleration due to gravity, the little g. So that's our big G, and it has units of meters cubed over seconds squared kilograms. I know people write this in, but that's very inconvenient. So the next unit we will look at will be C, and just get it out of the way. Speed of light, measured first, well, measured by Huygens anyway. Galileo tried to measure it, but it was too quick for him. Romer measured it using the moons of Jupiter, and Fizeau measured it using liquids flowing, and I guess, yeah. So the speed of light, that's an easy one to get out of the way. Okay? The G we got out of the way. The C we got out of the way. Now let's look at this. People don't often tell students that the units are not explicitly stated. You'll often see this in the books as the fine structure constant. Students all across America, the world, they go away trying to evaluate the fine structure constant, putting in all the charges and the H and the C that they know, and they don't get it to be dimensionless, or they don't even get that number anyway, because somebody who's teaching them didn't tell them that's not the exact value of it. That's using this quantity. Different units of electric charge. Nobody told them that. They go waste time. It's terrible. Students are often told that, oh yeah, R equals 2m. What's that? This defines the Schwarzschild radius, or the event horizon of a black hole when it crops up. R equals 2m. Wait a minute. Students go away and put in the m and they don't get an R, right? There's a G and a C missing here. So what formula is it? G squared, C cubed. We'll put in letters A and B and find the A and B by dimensional analysis. Now I don't use this kind of thing. I just use seconds, kilograms and meters. We want to find out what is the form of the M here. Well, R is meters to the power of 1. We have meters on the left-hand side. We do not have time, and we do not have mass on the left-hand side. But we do have mass on the right-hand side. And we do have the G to the power of A. And we do have the speed of light to the power of B. Well, the speed of light is meters over seconds, and the G is meters cubed over seconds squared kilograms. So now we write dimensionally consistent equations. So for the meters, I get meters to the power of 1 on this side is meters to the power of 3a plus b on the other side. And for the seconds, we have 0 on the one side equals seconds to the power of minus 2a on here, and minus b on the other side. And for kilograms, to the power of 0 on the left-hand side to the power of 1 plus minus a on the other side. So now from this we get dimensionally consistent equations. Well, it's very easy. A is going to be 1. So B is going to be minus 2, and that fits in. One equals 3 minus 2, sure. So now we know that A is going to be 1, and B is minus 2. So R equal 2m is really saying R equals 2gm over c squared. All right? Reinstating the units that we prefer to have in there. Very good. Now we're going to look at the other units. Let's begin with H. Actually, let's begin with the Planck length. So Planck's units are joules seconds. Joules are kilograms meters over seconds times meters. So kilograms meters squared over seconds squared times seconds. Kilograms meters over seconds, they're the base units. And this is the reduced Planck's constant. So h is 2 pi h cross. All right. So is that the fundamental unit? Well, it's possible that where does it come from? Equals hf. H times the frequency is the energy of a photon. We know this. All right. But really it comes up in Planck's radiation law. something like that. Okay? Actually, let's put the rest of it in. That's going to be the end. Planck's radiation law will crop up in a minute. All right, so here's the Planck length. Now, let's do alpha actually. Now, the fine structure constant will help us relate Planck length to the Stony length. And this is after George Stony. When did he live? I'm not sure actually. He was in Ireland anyway, 18th, 19th century. He was a great guy actually. I've talked about him earlier on when I do Stony units. Now Stony units, I forget what they have the form of, but I know how to get them. But I'll just look them up to save time. And I'm not saving time. Guess. Now actually I've done Stony units way back in an entire lecture, and I can go from LP, let's do this, okay. Let's multiply LP squared by alpha. Multiplied by the fine structure constant. Now the fine structure constant is E squared over 4 pi epsilon 0 H cross. Okay, see what happens? The H cross is eliminated. Now this is called a Stony length. Well, wait a minute. It also gives us a way to talk about, which is the most fundamental object. Is it the, Planck's constant or the universal unit of charge? Let's see what I mean by that. Here we have alpha equals this quantity here. So therefore then, since alpha is dimensionless, it can have the h talk to the e squared, right? Now, is this the most fundamental object instead of the h? So therefore I can write the energy of a photon that way instead, leaving out the Planck's constant, just replacing the fundamental unit of charge. Fundamental unit of charge is 1.6 by 10 to the power of minus 19 coulombs, measured by Millikan using the oil drop experiment. Wait a minute, if there's a fundamental unit of charge, why not a fundamental unit of mass as well? I don't know. Anyway, that could be what's cropping up in our equations all the time. We just get used to writing it as h cross RH. Alright? So now, what other units do we have? I've dealt with the h, and I've dealt with the h bar. The fundamental unit of charge is next. Well, it's cropped up. I want to keep this object because I need it for later. Now this is the Planck's radiation formula. Okay, so C, we got E. 1.6 by 10 to the power of minus 19 coulombs. And we've covered that. Let's cover the sigma. I take a sphere of iron hanging out at the ceiling, and let's say it's at room temperature. I turn off all the lights and there's no radiation in the room. That sphere is radiating energy around the room, and a snake could see it, right? It's in the infrared. If I heat the sphere up, it'll start to glow and you can see it emitting its own radiation, and it will go through a range of different colors because it is emitting radiation proportional to the fourth power of temperature in Kelvin, right? Now if I double the area, the surface area of the same iron sphere, I'll double the power, I'll double the output. Now here, this is the emissivity. I'm going to assume every time we work with black holes that the emissivity is going to be 1, so I can drop it out of the equation. A is the surface area, could be the surface area of a black hole, could be surface area of some emitting body, and sigma is a constant. I forget what it is. 10 to the power minus 8. Watts per square meter per Kelvin to the fourth. And it's called Stefan Boltzmann's constant. Well, it is a constant, but you can derive it. And one of the crowning glories of modern quantum theory is that we can go, what is the power of an emitting body? Well, it's a black body, it's emitting wavelengths over all the wavelengths. And there's a factor of 1 over 4 C. I think that should be cubed. Let me check. H cubed. No, C squared. Okay. Now Boltzmann's constant is in this beta here. Beta is 1 over kT. C squared H cubed. That is the sigma. We work it out. One of the crowning glories of this particular theory. Now the other thing that we have to look at is Boltzmann's constant. That's another constant, and that will involve R and NA. So these ones we will treat together. We've done that one. We've done all of those. So we get rid of this. We're nearly finished. Did I say that I got a wrong year for John Mitchell the last time? I had him down for living only 1 year. His years are 1749 to 1827. Yesterday, made a mistake. Let's look at Boltzmann's constant. .38 anyway, by 10 to the power minus 23 joules per Kelvin. K is a measure of the number of joules per Kelvin per particle, right? And it's defined as follows. It's R over NA. And what is R? Well, PV over T is the universal gas law. And it's equal to R for 1 mole, or NR for n moles. And R is 8.31 joules per Kelvin, is the universal gas constant. Sure I got that right? 8.314. All right, per mole, of course. Okay, so R over NA is going to be the K. So I can write R equals NA times K. Now, N is the number of moles, and that's the Avogadro's number, 6.02 by 10 to the power of 23 molecules per mole, particles per mole. So 2 moles is going to be 12.04 by 10 to the power of 23 molecules. 3 moles, 4 moles, 5 moles. This is counting moles. This is the number of particles per mole. So this is the total number of particles in a sample of gas. So in terms of Boltzmann's constant, PV equals nKT. That's where K crops up, and K also crops up in this one. If I count the number of microstates in a gas, whatever that means, the entropy of the gas is proportional to the log of it. K, I use a thing called W, by the way. And W is dimensionless because entropy is joules per Kelvin. And the units of K is joules per Kelvin. So really all this is doing is it's making this quantity dimensionless if I want to talk about pure information. And I'll talk about that later. That's coming up, okay? So now what have I done? I've addressed all the constants that are going to be cropping up when we study the thermodynamics of gases, so that you have a background in that. All of these things are really important. I know people who write the books don't emphasize them. They put in the units and have you look at them all right, but then it's covered under the counter. And theorists drop the fundamental constants in their calculations to save handwork. But then a student comes along to look at it and they don't know how to get the constants back in. I showed you how to do that. Let's leave it at that until I come back to the next one and we actually do look at the thermodynamics of black holes, right? Now I'm going to talk a little qualitatively about black holes. I hate doing that. I like to calculate everything. The talking becomes meaningless. But I have to, because otherwise I'll be getting into integrating, like what's inside a black hole, stuff like that. Nobody knows. So we have to talk about that later.